Welcome to day 2 of Introduction to Fluid Flow. Today we'll be discussing what is the continuity equation, derivation of the compressible and incompressible continuity equations, physical meaning of divergence, and application to streamlines. Let's start with the continuity equation. The continuity equation goes hand in hand with the conservation of mass, meaning mass cannot be created or destroyed in a fluid flow. So whatever mass enters a region, usually we call it the control volume, must either stay or exit. It can't just disappear. To visualize this, imagine water flowing through a pipe. If the pipe narrows, the water speeds up to maintain the same amount of water going in and out. That's the core idea behind the continuity equation. For incompressible flow, where density is constant, the equation is A1V1 equal to A2V2, where A is the area of cross-section of the pipe and V is the velocity of the fluid. This tells us that if the area gets smaller, the velocity increases to keep the mass flow same. An example would be if air flows through a pipe and enters an area of 2 meter square at a velocity 3 meter per second and it exits at an area of 1 meter square, then the velocity of the fluid should be 6 meter per second. In general form, for compressible flows like those in high-speed aircraft where density changes, the continuity equation is dou rho by dou t plus del dot rho v equal to 0. For incompressible flows such as low-speed aircraft where density remains constant, it simplifies to del dot v equal to 0, which means the divergence of the velocity field is 0, no net accumulation of mass. The physical meaning of divergence is that the net volume of fluid flowing out of a point is equal to the volume flowing in, so that the flow is balanced and the mass is conserved. Application to streamlines. For steady incompressible flow, streamlines don't cross, they show the direction of velocity. Since density is constant, if streamlines get closer, velocity increases. This helps us visualize airflow over wings, nozzles, diffusers, etc. For an example, flow over an airfoil, streamlines bunch at the top giving higher velocity and spreads out at the bottom giving low velocity. This behavior aligns with Bernoulli's principle and also supports the continuity equation. And that's it for today. If you learned something new, don't forget to like, share, comment and subscribe. Thank you for watching.